Hi everyone, it's Mrs. Meehan, and in this quick little screencast, I'm just going to go over a little bit about conservation of energy and then some practice problems. So let's think about a scenario here. So conservation, the conservation of energy just means that energy is conserved. It's neither created nor destroyed. So if you have a closed system, the amount of energy in that system will always be the same. If you have an open system, where something comes from outside the system and does work, you could actually increase the energy of that system, or energy could leave an open system. So let's just think about that. So in this scenario, we have a roller coaster and it's at the top of a track, and the track is 80 meters high. How fast will it be going at the bottom of the hill? So we have that roller coaster just to visualize it here. So it's at the top of that hill, and we want to figure out the velocity at the bottom of that hill here. So looking at the energy equation here, or the conservation of energy here, we know that if we have an initial energy and then we perform work, which would add energy to the system, that would equal a certain final energy that would be greater than the initial. If we did negative work, that would remove energy, let's say, and you would end up with a final energy lower than initial. But in this case, we're going to say that we're going to have the initial energy is going to be equal to the final energy, since work is going to be equal to zero. We're not applying work to the object. So at the beginning here, we can say that the initial energy is gravitational potential energy, since it's at the top of the hill. So that's going to be the initial energy of the system will be equal to GPE. And the final energy is going to be kinetic energy, since there will be a velocity now and no height. So up here we'll have a height, no velocity. Down here we'll have velocity but no height. So we can say that the GPE will be equal to the KE, the kinetic energy. Now the equation for gravitational potential energy is mgh, so we're just subbing that in. For kinetic energy, it's half mv squared. Rearranging it a bit. So if you do, let me choose a different color here, just to rearrange it. So to get rid of the half, you would just multiply by 2 and divide by m. So 2 over m here, multiplied to both sides. You'll notice that mass will cancel out completely. So we're canceling that out. So what you end up with is just the v squared is equal to 2 times gh, so the gravity times the height. Now when we put in the numbers, we have the v squared now is equal to 2 times 9.8 meters per second squared times the 80 meters in height that we were given. Then we need to find the square root of both sides, remember, to get just velocity, which gives us a velocity of 39.6 meters per second. Let's try a couple of practice problems here. So roller coaster has a velocity of 25 meters per second at the bottom of the first hill. How high was the hill? 32, 35, 41, or 56 meters? So going back to conservation of energy here, we have to say that the kinetic energy is going to be equal to the gravitational potential energy. So whatever that initial energy was, it's going to be equal to the final energy. So initial energy is going to be GPE, final energy is the KE, there at the bottom of the hill. So subbing in for the equations and then solving for H. The way to do that So divide by mg on both sides. Now you'll notice we have m here. We'll actually end up canceling out on both sides, mass, leaving gravity. So you end up with the height is equal to velocity squared divided by 2 times the gravity, or half times velocity squared over gravity, however you want to write it. So you sub in the numbers, and that gives you about 32 meters. A roller coaster has a velocity of 50 meters per second at the bottom of the first hill. How high was the hill? So similar to the last question, we just have a greater height this time. The height last time, or a higher velocity, sorry. So greater velocity here. Same exact method of rearranging the equation, where you end up with height is equal to velocity squared divided by 2 times the gravity. You end up with 127 meters, or 130 meters rounded. So answer D. How much work is done in stopping a 5-kilogram bowling ball rolling with a velocity of 10 meters per second? Okay, let's take a look here. So in this case, we need to figure out how much work is done. Now, work is the change in the energy. So in this case, since we have a bowling ball that has a velocity, and we're going to change the velocity, we're going to be talking about kinetic energy. So work in this case is going to be equal to the change in that kinetic energy. Now, if we write that out, I'll put it over here. So kinetic energy is half mv squared, and we'll call this the final velocity. So half mv squared minus half mv initial squared. So we can use this to calculate the work it takes to stop the bowling ball rolling with the velocity of 10 meters per second. Now, the ball is starting with a velocity of 10 meters per second, and it's going to end up with a final velocity of 0 meters per second. So, considering that, this ends up being 0, kind of canceling out this whole part of the equation. So to calculate the work, we could say it's equal to negative half m initial velocity squared. So we have our negative times the mass is 5 kilograms times that initial velocity here squared, 10 meters per second. And that's similar to what you're seeing down here in this box. Written a little bit differently, you can write it either way. You could say work is equal to half m change in velocity squared, and write out within parentheses the final velocity minus initial. Still ends up being the same answer. So in this case, we're just going to say it's 250 joules, which gives you answer D. How much work is done in stopping a 5-kilogram bowling ball rolling with a velocity of 20 meters per second? So similar to the last question, same exact process, where ultimately you could just solve for change in kinetic energy. You could do it the way I showed on the previous slide. You could do it this way, that's written in the box. Either way works. And you end up with about 1,000 joules. In this case, it's specifying the direction in the answer choices. So more accurately, it would be negative 1,000 joules. In the previous question, it didn't get that specific, but for this one we are. Why is it negative? Because we are lowering the velocity. So in order to do that, the work that is done is in the opposite direction as the velocity of the bowling ball. Now notice how this is negative 1,000 for stopping a bowling ball that is rolling 20 meters per second compared to 250 joules for the bowling ball rolling 10 meters per second. Way more than double. Even though the velocity is doubled, we see quadrupling of the work needed to stop it. And that just goes back to the equation and the fact that velocity is squared in that equation. So if you double the velocity, that correlates with 4 times the energy on the other side. So when you are driving, think about the fact that the faster you're going, the more work it's going to take to slow you down. And the more work that is going to take, the more distance it's most likely going to take to stop. Practice problems that go along with this lesson include the chapter problems number 65 to 67, 69, and 71 to 76, multiple choice 24 to 30. Those are posted to Google Classroom. If you submit your answers to any of those problems, you will get participation points.